All right, let's dive right into this explainer, because today we're unpacking one of the absolute most foundational paradoxes in all of computer science. You know, we rely on computers because they're precise, deterministic machines. You give them a math problem and they're going to give you the exact same answer every single time. But what if I told you that the second you introduce concurrency, doing multiple things at once, that fundamental, rock-solid mathematical reliability can just shatter? Well, it can. Today, we're exploring process synchronization.
Picture this. It's a classic mathematical brain teaser, but it actually strikes right at the core of what we're talking about today. Imagine a shared variable, just a really simple counter set to 5. Now you have two programs running concurrently. Program 0 adds 1 to the counter. Program 1 subtracts 1 from the counter. Basic elementary arithmetic tells us that 5 plus 1 minus 1 equals 5. Obviously, right? But in the world of computing, that expected answer of 5 might magically become 4 or even 6. So how does basic arithmetic completely break down like that?
Well, to figure it out, we've got to look at the reality of the devices we literally use every single day. This terrifying paradox isn't just some abstract theoretical anomaly. It's happening right inside the modern multi-core processors powering whatever device you're watching this on right now. Here's the thing. Programs execute concurrently. They share memory, and crucially, they can be interrupted at any fraction of a millisecond. When two programs try to access and manipulate the exact same piece of data at the exact same time on different cores, well, data consistency just completely flies out the window.
Let's actually put this in slow motion and watch the train wreck happen play by play. Program 0 steps up to the plate and reads the counter into its register. It sees a 5. But wait, right before it can actually do the math, boom, a context switch happens. The CPU jumps over to Program 1. Program 1 reads the counter into its own register. It also reads a 5. Now Program 0 resumes, adds 1 and saves a 6 back to memory. But Program 1 is still holding on to its own outdated copy of 5. It subtracts 1, gets 4, and just brazenly overwrites the memory with 4. The two programs have completely crashed into each other, and just like that, our data's corrupted.
Section 1. The Villain and the Law. Defining race conditions and critical sections.
Okay, so before we can solve any problem, we have to name it, right? This chaotic phenomenon we just saw? That is called a race condition, and it's basically our main villain today. It threatens data consistency literally everywhere. In a race condition, multiple processes are manipulating the exact same shared data concurrently, and the final state of that data depends entirely on the completely unpredictable order in which those instructions happen to execute. To stop this madness, we desperately need synchronization. And the actual battleground where this villain strikes? It's elegantly defined as the critical section. This is the exact danger zone where shared variables get updated, where files are written, where things can go horribly wrong. All the surrounding code you see, the entry section, the exit section, the remainder section, those are just the administrative borders. The goal here is simple to say, but incredibly difficult to pull off. When one process is inside its critical section, absolutely no other process can be allowed inside theirs. Period.
So to actually fix this critical section problem, computer scientists laid down the law, a framework of 3 unbendable rules for any valid solution. First up, mutual exclusion. If a process is in its critical section, no one else gets in. Exclusive access. Second, progress. If nobody is in the critical section and someone wants to enter, the system cannot indefinitely postpone the decision of who goes next. It can't just freeze up. And third, bounded waiting. Once a process asks to enter, there has to be strict mathematical limit on how many times other processes can cut in line before that request is finally granted. Basically, no process gets left in the waiting room forever.
Section 2. The Software Struggle. Iterative Failure to Success.
All right, armed with those 3 laws, early computer scientists tried to write pure software to control the chaos. Let's look at this messy trial and error struggle. Compare these 2 early attempts. On the left, attempt 1 uses a single turn variable, like, it's your turn, now it's my turn. On the right, attempt 2 uses flags. Basically, hey, I'm raising my flag, I want to go in. I'll pose this to you. Do either of these actually work perfectly? Do they survive every single weird timing edge case without breaking those 3 laws we just established?
The wild answer here is no way. They absolutely don't work. Pure software solutions are surprisingly messy and super fragile. If you only use turns, you end up with strict alternation. Process 0 literally has to follow Process 1. So if Process 1 suddenly doesn't need to go in anymore, Process 0 is locked out forever. Progress rule? Broken. On the flip side, if you use flags without turns, you can hit this crazy timing fluke where both processes raise their flags at the exact same microsecond, see each other, and both just politely wait forever. Deadlock. Once again, progress is totally violated.
But all that iterative failure wasn't for nothing. It eventually built up to this absolute masterpiece of logic, Decker's algorithm. Decker realized that to win, you have to combine the flags and the turns. You declare your intent by raising a flag, but if there's a conflict and both flags are up, you look at the turn variable to break the tie. It's a brilliant victory using nothing but basic programming variables. But here is the catch. It is incredibly complex. And as computer systems rapidly grew from single processors to massive multi-core beasts, these pure software locks just became way too cumbersome to manage at scale.
Section 3. Hardware to the rescue. Uninterruptible atomic power.
So, to really fix this at scale, we had to shift the responsibility away from software and down to the physical silicon itself. But hold on, before we look at the modern fix, let's test your logic for a second. This whole problem starts because the CPU interrupts a program mid-calculation to do a context switch, right? So why don't we just tell the CPU to temporarily turn off its interrupts while we update the counter? No interruptions, no race condition. Sounds brilliantly simple, doesn't it?
Yeah, it's a total trap. First off, handing a random user application the power to literally shut off the CPU's interrupt system is dangerously irresponsible. One tiny bug could freeze the entire computer permanently, but more importantly, it completely falls apart on modern multi-core systems. Even if you disable interrupts on Core A, Core B is still happily running. Core B can still barge right into the shared memory and ruin the data. Disabling interrupts is definitely not a scalable answer.
So instead, we get our hardware hero. Rather than relying on massive software algorithms to check locks, modern machines provide specialized hardware instructions to do it in one swift, unblockable strike. These instructions, like test and set, are literally baked right into the silicon of the CPU.
Now let me break this down in the simplest possible way, like teaching a total beginner. The magic word here is atomic. And no, atomic doesn't mean explosive in this context. It means indivisible. When the hardware executes an atomic instruction, it guarantees this unbreakable protective bubble around that action. It cannot be interrupted midway, not by a timer, not by a different core, nothing. It either completes entirely or not at all. The hardware physically guarantees that no sneaky context switches can happen while this specific instruction is firing.
Let's actually walk through this step by step to see how it mathematically guarantees mutual exclusion. When a CPU calls test and set on a shared lock variable, the hardware itself steps in. It temporarily locks the memory bus. It reads the current value of the lock, instantly overwrites it to a 1, which means locked, and returns the original value it just saw. Because it's purely atomic, if two CPUs fire this instruction at the exact same nanosecond, the hardware physically forces one to completely finish before the other even starts. The first CPU sees a 0, sets a 1, and boldly enters the critical section. The second CPU gets in line, sees that 1, and knows it has to wait. Boom! Race condition defeated.
Here, you can actually compare the two giants in the world of hardware locking. Test and set is kind of the brute force method. It just hammers a 1 into the target variable no matter what, and then checks what it overwrote. Over on the right, we have compare and swap. This one is much more elegant. It only swaps in the new value if the current value matches what we actually expected to find. If the lock is 0, make it 1. If it's already 1, do nothing and let me know. Both of these atomic powerhouses are super simple to verify, and they scale absolutely flawlessly across massive multi-core processors.
Section 4. The catch. Unresolved bounded waiting.
You know, there's almost always a catch in computer science, right? Hardware locks are phenomenal, and they completely guarantee mutual exclusion. They lock down the data. But a raw, simple test and set loop does not guarantee bounded waiting. Just think about it for a second. If you have 10 processes spinning in a loop, hammering the lock variable, frantically waiting for it to turn to 0, when the current process leaves and resets it to 0, which of the 10 spinning processes actually gets it next? Well, it's completely random. It depends entirely on which hardware cycle happens to hit the memory bus first.
Which leaves us with this final, incredibly thought-provoking problem. We've successfully used hardware to stop data corruption. We stopped the villainous race condition. But because the hardware selection is totally random, a deeply unlucky process could theoretically lose the race for the lock over and over and over again, waiting in line forever while other processes just keep happily jumping ahead of it. We saved the data, sure, but we created a system where an application might literally starve to death just trying to get a turn. So how do operating system designers build fair, complex queuing systems on top of these raw hardware locks to prevent that starvation? Well, that is a brilliant open question to ponder as you look deeper into operating systems design. Thanks so much for joining me for this explainer, and I will catch you in the next one.